So how do we handle sign numbers? Okay. Now, I said you and I deal with negative values. How does the machine deal with negative numbers? Like a -3. So when you start dealing with positive and negative numbers, we're dealing with sign numbers. Well, we can fix that. This is one way to do it. Normally, you can put 0 for positive numbers in the last bit on the left. If you put a 0, that number is positive. If you put a 1 for that number, that's a negative number. That's a sign bit. That's not part of the number. So the last location will make it either positive or negative, a 0 or 1. If it's 0, it's going to be a positive number. If it's 1, it's going to be a negative number. -3. Notice I'm using the last bit to indicate positive and negative. Now, the problem with that, when you take a bit and put it aside for that, you just shrunk the size of your numbers that you can use. So here's an example. If I decided I'm going to use a 5 bits, and this bit is going to be the sign, this bit. So I got 1, 2, 3, 4. So this is my sign here. If that bit here is 0, the number is positive. If that bit is 1, the number is negative. So if I want to write plus 10, 1, 2, 3, 4, and the sign 1. 1, 2, 3, 4, and this is the sign here. 10 is what? 2 and 8? 0, 1, 0, 1. 8 and 2, that's 10. Because this number is positive, then this sign will have to be what? 0. 0 means positive number. 1 means negative number. If I want -13, again, this is the sign. I know it's negative, I'll put a 1 in it. 13. 8 and 4 and 1, is it? 1, 0, 1, 1. Yes?
So, to avoid confusion now, for a signed number, do we just assume from now on that if there's a 0 and 1 in front of a binary number, that's a signed number? Because in the past, we would add that.
Correct. Let's wait on that. Let's wait on that statement. Because there's multiple ways. You're going to see what other ways of doing it. Yeah. But if you have a 1 usually at the end on the left side, that's an indication that number is a negative number for now. Yes. If you have a 0 for this section, that number is a positive number. Before, you're right, that was 1, 2, 4, 8, 16. We looked at that number, it's 16. We didn't deal with negative numbers. We're saying in real life we have positive and negative. How do you differentiate between them? So this is not 16 plus 8 plus, what's that? 1, 2, 4, 8. 16 plus 8 plus 4 plus 1. It's not. This is a negative because of that 1 here. 8, 4, and 1, that's negative 13. The problem with that, go ahead and write -18. You can't. Not with 4 bits here. Doesn't fit. So taking that bit for a sign, I just shrunk my number. The maximum number I can use in this case is really 15. Positive or negative.
So that 1 bit takes up that space.
Well, normally that's the next 1, 2, 4, 8, that's a 16. If I'm allowed to use it, then my biggest number is going to be 16 plus 8 plus 4 plus 2 plus 1. 16 and 4 is what? That'll be 31. So right now the biggest number is 15. By eliminating this one, if I'm allowed to use this one, I can go now to 31. 1, 1, 1, 1, 1. That number can be 31. So okay, well, have another one with the same story. If I use another one for the sign here, now the maximum is plus 31 or negative 31. But if I can use the one after it, I can go instead of 31 now to what? 63 or 64. 63 will be up because 1 will be for the sign. So each time you take a bit per aside, you shrink the biggest number you can use there. And you won't be able to add them. So if we look at, let's pretend now we're going to use sign numbers. Here we go, the rule for addition. It says if you want to add numbers, sign numbers like this, in each of these examples, we must determine which is the larger magnitude. Now, thus, we must subtract the smaller from the larger and finally attach a sign to the number. So if you're adding two negative numbers, if you're taking two negative numbers and you add them together, that's a -8. I might be outside the range. If one of the numbers is positive, one is negative, I don't have that problem. You will not have an overflow problem if one number is negative, one number is positive. Because why? You're going to subtract. But when both numbers are the same sign, there's a chance now you're going to be overflow. Either both positive and both negative. So let's take a few examples and see. I'm going to use 3 bits for the number and 1 for the sign. 3 bits, so I'm using for all these numbers, 3 bits for the numbers, and this is the sign. Let's begin. So the biggest number I can put there is 1, 1, 1, which is what? 1, 2, and 4, that's 7. So if I take plus 5, plus 3, I got a problem. Because what's that number? Plus 8. Can I fit a plus 8 in this? No, I can't do it. Too big. I don't have room for it. The biggest number I can put plus or minus 7. Can I do minus 5, minus 3? Negative 8. Too big. So when the two numbers have the same sign, I have a little problem. Now, if they have different signs, I'm okay. Because what's that number?
-2.
How about plus 2? Yeah. Or if you have, let's say, 3 minus 5. What's the answer? Negative 2. I'm okay. So the only time I'm going to have a problem when both signs are the same. I could have a problem. It's not always the case, because if it's 2 and 3, they're both positive. What's 2 and 3? 5. Is that number too big? No. The only time will be too big if you exceed the size, in this case 7. 8 exceeds the 7, I got a problem. If I go, what's biggest number is 7, what's 6? Plus 4. I got a problem now. That's 10. This one is too big.
So it can't equal 8, correct?
It has to be under. For me to use that sign numbers, that number has to be under between plus 7 minus 7. 1, 1, 1, that's a 7. When this sign is 0, that's positive. When this sign is 1, that's a negative. So that's a plus 7. That's a negative 7. This is not a number. This is just a sign. So I'm limited by these two numbers with that. Okay. So right here, we must subtract the smaller from the larger and finally attach the sign of the larger magnitude. When you're adding numbers, that's how we do them. Now, another way of doing that is something known as the 2's complement. See that 2's complement here? Signed binary numbers are nearly always stored in 2's complement. How do you store a negative number? We don't want to give that digit away. It's bugging me to give that digit away. I don't want to give it up, because I'm limited now by plus or minus 7. So I can store the numbers in 2's complement. So let's talk about 2's complement. There's an equation how to find the 2's complement. And it says the 2's complement, to find it, which I never do it that way, can be found by equal 2 to the power of n minus 1 minus 1. What does that mean? If I have a 4-bit machine, 4-bit, I'm not using sign here. I got 4-bit, and I want to write the number 7 or negative 7. I'm not holding this as a sign. I'm not using that for a sign anymore. I want to write the number 7. I got a 4-bit machine. The way you're going to write the number 7, the 2's complement, you're going to find what that number is. Actually, 2 to the n minus the number. That's the 1's complement there. 2 to the n minus the number. Let me just write number. So how would I write minus 7? All right, guys, 4 digits. What's 2 to the 4? That's 16. 16 minus the absolute value of the 7, actually, the negative 7. The absolute value of that, which is a 7. What's 16 minus 7? 9, 8, and 1. And that's that number. Now, nobody does it this way. There's not a single person I know that does it this way to find the 2's complement. Nobody even remembers that equation. I had to look at the book and see, how do you find the 2's complement of a number? I don't remember it, because there's an easier way. To find the 2's complement of a number, you have 4 digits. 2's complement of negative 7. We take the 7 and we give the 1's complement. First, here's the 7. What is 7 in binary? Not a negative. What is 7 in binary? Using 4 digits. 0, 1, 1, 1. Right? That's a 7. The 1's complement, you change all the 1's to 0's, all the 0's to 1's. So take that number, change all the 1's to 0's, all the 0's to 1's. You'll have what? 1, 0, 0, 0. So that's step number 1. That's step number 2. Step number 3, add 1 to step 2. Let's add 1. When you add 1 to that answer, what do you have? 1, 0, 0, 1. Is that what we got a few minutes ago? 1, 0, 0, 1. So we can find the 2's complement of any number by using, take the number, change it to binary, do the 1's complement, add 1 to the answer. That's how everyone does it. So you will not see me talking about sign numbers. I will not be holding a spot for the sign. I'm going to store that as this number. This is not a sign. Once I see the 1 there, that tells me that's a negative number. To change it back to the positive, we do the 2's complement of that answer again. We change all the 1's to 0's, all the 0's to 1's, and we add 1 to the answer. So what is the 2's complement? Let's talk about this for now. Of negative 5. Take the 5 in binary. I'm using 4 bits here. What's 5? 0, 1, 0, 1. What's the 1's complement?
1, 0, 1, 0.
1, 0, 1, 0. Add 1. What do we have? 1, 1, 0, 1. That's the 2's complement. Of negative 5. That's how the negative 5 will be stored in your 4-bit computer, using the 2's complement. Why are they using the complement? Because you'll find out shortly, if you don't use the complement, then when you're adding and subtracting, you got to have two devices, one for addition, one for subtractions. By using the complement, we can use the same device to add and subtract. The same gizmo will add and subtract the stuff for us. Okay, let's try a couple more. Take a minute. Tell me what the 2's complement of -1. Yep, somebody said 1, 1, 1, 1. Because you start with the 1, and the 1 is what? 0, 0, 0, 1. The 1's complement will be what? 1, 1, 1, 0. Add 1 to the answer, what do we have? 1, 1, 1, 1. That's a 2's complement. Two's complement of -0. Let's try that too. Zero is what? 0, 0, 0, 0. 1's complement is what? 1, 1, 1, 1. Add 1 to it. 0, 0, 0, 0, 0. And we have an extra carry, right? I'm using 4 bits. That carry is gone. So that's the 2's complement. It's 0, 0, 0, 0.
Is that because of the fact that 0 is not really positive?
-0 and +0 is the same thing. That's why I end up with the same answer. Now, we said the nice thing about this is I can use the same device, and that's what the book is saying. The reason that 2's complement is so popular is the simplicity of addition. To add any two numbers, no matter what the sign of each is, we just do binary addition on their representation. Straightforward, just binary addition. We do not differentiate. If the number is negative, we take the 2's complement of it, and we add them. And let's take a few examples, see what will happen.
How do you know if it's already a complement or not?
You'll see in a minute in the circuit, you don't know if that's complement. You type in the number in your program, you might have something coming up. You got to do the complement. You got to check and see if that bit is a 1 or a 0 when you write it in. And you actually do the programming on that. You know, when you push that minus sign on your keyboard, you got to have some piece of program that says complement that number. You know. Now let's take a few numbers and go through them and see. One more thing it says, sometimes, because if the last digit is 1, you'll notice at the end, if you have a 1 at the left side, it looks like a negative number. But sometimes whenever we add two positive numbers, because that number is going to get big, right? And you might have an overflow. That overflow is going to be a 1. Each beginning with the 0, and get a result that looks like a negative number beginning with 1. Because you have an overflow, there is an overflow. And the same thing if you add two negative numbers, at the end, you're going to have a 1 and a 1, you're going to add them, it's going to say 0 carry 1 or 1 carry 1. So the last one is going to look like a negative number when it's really just an overflow. We have to be careful with that. And we'll give you some examples, you know. So let me take, let's say I want to add -5 plus 7. We know the answer is what? Plus 2. Now, the way we add them now, it's a 4-bit machine. Remember, we have a 4-bit machine. I need to find the 5 first. The 5 is what? 0, 1, 0, 1. I need to find the 1's complement of that. What's the 1's complement? 1, 0, 1, 1. 1, 0, 1, 0, right, for now? You add the 1. Add 1. Let's get the 2's complement. What do you have? 1, 0, 1, 1. That's 1, negative 5. And 7, that's a positive number. 0, 1, 1, 1. Let's see what happens when we add them. 1, 0, 1, 1. Add to it 1, 1, 1, 0. Remember, it's a 4-bit machine. 1 and 1. 0. Carry 1. 1 and 1 and 1. 1. Carry 1. 1 and 0 and 1. 2. 0. Carry 1. 1 and 1. 2 and 0. 0. Carry 1. If you discard the carry, what's your answer? Positive 2. So that carry, move it all the way to the right, drop it, and it'll be coming up here. And the answer is plus 2. Here's the rule. For signed numbers, the carry out of the high order bit is ignored. See that? And you have an overflow if we're adding two positive numbers, two numbers of the same sign, two positive or two negative numbers. For unsigned numbers, the carry out of the high order bit is an indication of overflow as an addition. However, in subtraction, a 0 indicates overflow. You're going to see some example with overflow. Now, there was no overflow in some of the examples. We're going to do some with no overflow. What do we do with that? The carry out of 1 indicates no overflow for unsigned numbers. So let's try some of these. So it says the carry when the numbers are here, ignore it, and add it when the signs are different. Let's take another one. Negative 5 plus 5. That's a 0, right? We know what negative 5 is. 1, 0, 1, 1. We know what 5 is. What? 1, 0, 1, 0. 1 and 1. 0 carry 1. 1 and 1. 0 carry 1. 0 carry 1. 0 carry 1. Ignore the overflow. What's your answer?
0.
0. So when the numbers are positive and negative, you're good. When they're the same sign, we might have a problem. Now, let's try another one. Now let's add the same signs. Let's add plus 5 and plus 4. What's the answer? Plus 9. 5, 0, 1, 0, 1. 4, 0, 1, 0, 0. 1, 0, 1, 1, 0, carry 1. What's the overflow? There's nothing in the overflow. 0. There's no overflow. But looking at that number, the 1 here, it looks like a negative number. When you do the 1's complement, all these negative numbers will have a 1 in the last place. So that tells me that looks like a negative number to me. Or try another one. What's a negative 5?
Why just having a 1 there make it look like a negative number? When it just, to me, it just looks like you have a positive 8.
Okay. Try this one. Let's look at this. What's that answer there? Negative 9, right? Let's look at the 5. We know what the 5 and 2's complement. That's what? 5 is 0, 1, 0, 1, right? Complemented 1, 0, 1, 0. Add 1. That's 1, 0, 1, 1, right? Watch this now. And let's take the negative 4. What's 4? 0, 1, 0, 0. Complement that. 1, 0, 1, 1. Add 1 to that. What do we have? 1, 1, 0, carry 1. 1 and 0, 1, 1 and 0, 1, 0 and 1, 1, 1 and 1, 0, carry 1. Is that sum of 7? If you just ignore the carry, is that sum of 7? Because you're saying the answer to me is 9, right there. So if you ignore the carry, just like it says when you add them, you ignore the carry. Is that sum of 7? No, it's not. So when you're adding the same sign, where is it? Here we go. For sign numbers, the carry out of the higher order bit is ignored and overflow occurs if the addition process operates on two numbers of the same sign. If you have the same sign, we have either carry 0 or 1 in this case, produce a result of the opposite sign. When the carry out of this, notice the carry is 0, you find. When the carry is 1, the result produce a number of the opposite sign. That says I have a carry of 1. That means my result is not this. My result for this has to be the 2's complement of that number. So when you're adding the same sign, if the carry out is 0, you find. That's a 9. That's what it's supposed to be. And it's 0, that means it's positive. When the carry is 1 here, it says this is wrong. And to find the answer to that, you do the 2's complement of that number. So what's the 1's complement? 1, 0, 0, 0. And you add 1 to that number. 1, 0, 0, 1. And it's not 9 because the carry is 1 here. It is a negative 9. That's what that number, that's a 9, but that tells me that's a negative number. For sign numbers, here we go, the addition operates two numbers, the same sign, produce a result of opposite sign. I'm adding two numbers of the same sign. Notice they both have 1s and then they're both negative. The result looks like it's a positive number. That says something is not right. For unsigned numbers, the carry out of the high order bit is an indication of overflow in the addition. However, in subtraction, 0 indicates overflow. We'll get to that subtraction. We didn't even touch subtraction. The carry out of 1 indicates no overflow for unsigned numbers. So let's try another one. Now let's do...
Can you go back for a second? Just go to the... Okay, I got it.
Let's try another example. I want to do 7 minus 5 now. Well, in math, you know that number is what? 7 plus what? Negative 5. That's the beauty of actually using the complement. I don't have to create a subtractor. We know what 7 is. That's 0, 1, 1, 1. We know what the negative 5 is. Here's the 5. 1, 0, 1, 0, 1. Change it 1, 0, 1, 0. Add 1 to it. 1, 1, 0, 1. One and 1. Carry 1. 1 and 1. 1 carry 1. 1 and 1. 1 and 1. 0 carry 1. Again, when the numbers are different signs, there is no, actually the answer is correct. We ignore the carry coming out of the last one. The carry out of the last one, the highest bit is this one, ignore it, and what's your answer? 2. When the two numbers for sign numbers, the carry out of the higher order bit is ignored when the two numbers are the same, different signs. One is positive, one is negative. That's a 2. Now if I do 5 minus 7, let's see what will happen. We know what 5, 0, 1, 0, 1, 7, so remember this is 5 plus a negative 7, so I got to find the 2's complement of 7, 1's complement, add 1 to it, one and 1, 0 carry 1, 1 and 1, 1 and 0 is 1, 1 and 0, 1, 1 and 0 is 1. And what's the carry coming out of that? For that number, the carry is 0. You're adding a positive to negative. That number is 1. No carry. That number is 1. That tells me something is not right. My answer should be the complement of that number. The 2 is complement of that number. And the complement of that number is 0, 0, 0, 1. Add 1 to it, plus 1. It's 0, 1, 0, 0, and it's a negative number. That number tells me it's negative. So when you're subtracting, adding different signs, there is no carry. The last one, you look at that digit, if that number is 1, that's it. Oh, your number is negative. You take the 2's complement, you stick a minus sign, that's a negative 2. It is. So you got a negative what? So this giving you the number in 2's complement. It is this tells you it's negative, but it's telling you in 2's complement. So to get the actual number, you got to take the 2's complement of that number, which is 0, 0, 1, 0. The value of that number is actually a 2. This tells you it's negative, but what's the value of it? You have to go back, take the 2's complement to get the value of that number.
But we're not looking at the remaining.
Nope. Now when the signs are different, we ignore that carry. Notice here, that's the 2 examples. I did 5 minus 7 and 7 minus 5. Now if I do 7 minus a minus 5, mathematically, 7 minus a minus, that becomes 7 plus 5, is going to give me a positive number. You're adding a positive to a positive. See, the 0 tells me it's positive, and the answer says is 1 here. It's like, uh-oh, something is not right. Just like this, that tells me the number is negative. So for unsigned numbers, overflow is indication by the carry of 0. The result of A, that's this one, which is the 5 minus 7, should be negative 2, which cannot be represented in the unsigned number. So yes, you take the 2's complement of that and you put the minus. Example 12b, that's this one. Overflow because the addition produces or process involves 2 positive numbers and the result looked negative. Notice positive and positive, the result looks negative because the 1 there indicates that the answer should be actually 12. But that's greater than the largest 4-bit you can put in there. Unsigned number, which is a 7. So a little bit tricky there. You have to look at them and see what you have for each one. Now we treat subtraction. I might have a picture of what actually a subtractor will look like. It's the same device. Oh, it might be later in the book. As I said, we use this device for addition and subtraction. me just